Hello everyone, David Angelo Bantugon here. Today I will discuss about the principles of electronic communication systems. This is the third edition of Louis E. Franzel Jr. I will discuss about the second chapter, which is entitled The Fundamentals of Electronics. The topics covered are the gain, attenuation, and decibels. Second is the tune circuits. Next is the filters, and lastly is the Fourier theory. Most circuits in electronic communication are used to manipulate signals to produce a desired results. And these signal processing circuits all involve a gain and attenuation. First is gain. What is gain? Gain simply means an amplification, and we can find the gain by dividing the circuit's output to its input, denoted by A sub V. We can find the gain by dividing the voltage output over the voltage input. From the figure below, an input signal comes through the amplifier and out comes the output signal. We can find the gain by dividing the output signal by the input signal by using its voltage. Next is power amplifiers. Since these amplifiers are related to gain, we can find the power gain by using the output over input formula. We'll just exchange the voltage values from the earlier equation to a power value. Here is an example. The power output of an amplifier is 6 watts. The power gain is 80. What is the input value? We are given by the formula A sub P is equal to output power over input power. Therefore, the input power is equivalent to output power over power gain. And by simply substituting the given values and by simple algebraic means, we can find the input power which is equivalent to 75 milliwatts. Next is cascaded amplifiers. The amplifiers can be cascaded when there are two or more stages or values that can be found or that is given that are connected together. What is cascaded or cascading? Cascading simply means the number of devices or objects that are arranged in a series or sequence. And we can find the overall gain by multiplying or finding the product of the individual gains. Here's another example. Three cascaded amplifiers have power gains of 5, 2, and 17. The input power is 40 milliwatts. What is the output power? By multiplying the 5, 2, and 17, we can find the power gain, which is 170. And by substituting the input power and the power gain, we can find the output power, which is equivalent to 6.8 watts. Next topic is attenuation. Attenuation is the loss that is introduced by a circuit or its component. Simply put, attenuation is somewhat reverse of a gain. As I said earlier, attenuation is related to gain. That is why it is also represented by the letter A, and it is also has the same formula, which is the output over input formula. Attenuation is a gain that has a value of less than 1 unit. From the given figure, by using the voltage divider theorem, we can find the gain, which in this case is 0.33. And since it is less than 1, it is classified as attenuation. From the given figure, the circuit has multiple values and can be cascaded. By multiplying the values, in this case, the output voltage is 32.4 millivolts. Decibels, as we all know, decibels is a unit of measurement related to the level of intensity based on hearing. In the case of electronics, it is used to express the gain or loss of a given circuit. Deci meaning 10. Therefore, a decibel is 1/10 of a bell. Next, here are the respective formulas for voltage, current, and power gain or attenuation. There's a given for voltage, for current, and for power. Here is an example. A filter has a power input of 50 milliwatts and an output of 2 milliwatts. What is the gain or attenuation? By substituting the given values to the formula of power gain, which is 10 logarithm of 2 over 50, we can find the decibel value, which is negative 13.98. As a simple reminder, if the figure is positive, that denotes a gain, otherwise an attenuation. Antilogs are the reverse of a logarithm. It is obtained when the given base is raised to the logarithm, which is the exponent. It is used to calculate voltage or power, wherein there is a given decibel gain or attenuation, and also includes the output or the input. The dBm and the dBc. A dBm is a decibel that is equivalent to a scale relative of 1 milliwatts. Next up is tuned circuits. Tuned circuits are all made of inductors and capacitors that resonate with each other at very specific frequencies. Reactive components. As said earlier, tuned circuits are all made up of inductors and capacitors. Opposition to alternating current flow offered by coils and capacitors are known as reactance. What is reactance? Reactance is the opposition of a circuit element to a change in current or voltage due to the element's inductance or capacitance. Next, next up is capacitors. Capacitors are originally known as condensers. It is a passive two-terminal electrical component used to store electrical energy temporarily in a electric field. And capacitive reactance, denoted by the X sub C, is the measure of a capacitor's opposition to an alternating current. Here is an example. What is the capacitive reactance of a 100 picofarad capacitor at 2 megahertz? We have the formula, which is 1 over 2 pi Fc. By substituting the given value, we can find the capacitive reactance, which is the 796.2 ohms. From the figure, the resistors are lead reactance and inductors lead inductance. As said earlier, capacitor tends to oppose voltage changes across them. That is why there is an R leakage. Inductors. An inductor, aka coil or reactor, is a passive two-terminal electrical component which resists changes in electric current passing through it. And a magnetic field is produced around the coil when a current passes through. This process has the effect of opposing current changes in the coil. This effect is known as inductance. Next, regarding inductors is the unit. The basic unit of inductance is Henry, denoted by the letter H. Opposition to alternating current offered by inductors is continuous and constant, and is known as inductive reactance, denoted by the X sub L. From the figure, these are the types of inductors. First is the heavy supporting wire coil. Next is the inductor made as copper pattern. Third, or letter C, is the insulating form. D is the toroidal inductor, which is the ring-shaped magnetic core of high magnetic permeability. Next is the ferrite bead inductor. Ferrite is a form of very effective filters for applications such as reducing the electromagnetic interference or EM interference. And last is the chip inductor, which is found in common circuits. Inductors. The inductive reactance, denoted by its X sub L, is directly proportional to the frequency and inductance. Here's an example. What is the inductive reactance of a 40 microhenry coil at 18 megahertz? From the formula of X sub L, which is equivalent to 2 pi 2 pi f 2 pi fl, and by substituting the given value 40 microhenry and 18 megahertz, there is the equivalent of 4522 ohms. Next is resistors. Resistors offers or gives almost or nearly pure resistance when subjected to low frequencies. A resistor's lead inductance and stray capacitance cause the resistor to act like a complex RLC circuit. From the figure, from the previous slide, a resistor's leads have inductance. So a resistor and its lead inductance is equivalent as stray capacitance. Next up is the skin effect. Skin effect is the tendency of electrons flowing in a conductor to flow near and on the outer surface of the conductor frequencies in the VHF or UHF and the microwave regions. As an analogy, think of the electrons as rust that clings to a pipe and it grows thicker as time passes. That is the same when the skin effect increases wire and inductor resistance at high frequencies. Next up is the tuned circuits and resonance. A tuned circuit is made up of inductance and capacitance and resonates at a specific frequency or the resonant frequency. What is resonant frequency? Resonant frequency is the natural frequency of vibration determined by the physical parameters of the vibrating object. The term tuned circuits and resonant circuits are used interchangeably. Series resonant circuits. It is made up of inductance, capacitance, and resistance connected in a series manner. It is often referred to as an LCR or RLC circuits, which is interchangeable positions. Resonant frequency is inversely proportional to the inductance and capacitance. It is equivalent to 1 half pi multiplied by the square root of LC. The first figure shows what a series resonance circuit looks like. The X sub L, X sub C, and R are all interchangeable since it is a series circuit. And the second figure is the graph regarding the relationship of reactance and frequency. Here is an example. What is the resonant frequency of a 2.7 picofarad capacitor and 33 nanohenry inductor? For the frequency, we will use the formula of 1 over 2 pi square root of LC by substituting the elements and the given values. We can find the frequency, which is equivalent to 533 megahertz. Next to the series resonance circuits is the bandwidth. In computing, it is the bitrate of available or consumed information capacity expressed typically in metric multiples of bits per second. While in electronics, bandwidth is used to measure electronic communication. It is often used as a term for the data transfer bitrate. The half power points is simply put the 70.7% of the peak value of resonance. The quality is the ratio of the inductive reactance to the total circuit resistance, while the selectivity is how a circuit responds to varying frequencies. Here from the figure we can see that the peak value is 2 milliamperes, and by multiplying that by 70.7% or 0.707 of the peak value, we can find half the half power points as 1.414 milliamperes, and we can find the bandwidth as f2 minus f1. From the figure, we can see the relationship of the quality on the bandwidth. As the quality increases, the bandwidth decreases, while if you decrease its quality, the bandwidth will increase. Next up is the parallel resonance circuits. It is formed when the inductor and capacitor of a tuned circuits are connected in a parallel with the applied voltage. It is often referred to as an LCR or RLC circuit, which is somewhat similar to the series resonance circuit. Resonance occurs when the reactance of an inductor balances the reactance of a capacitor at some given frequency. From the first figure, we can see what a parallel resonance circuit looks like. We can find its total current by adding the square of the inductor current and capacitor and finding the square root of its sum, while the second figure is the current relationships in a parallel resonance circuit. Continuing the parallel resonance circuits, at resonance, a parallel tuned circuit appears to have an infinite resistance. It also appears to have an infinite impedance and draws no current from the source. It also acts as an open circuit. However, there is a high circulating current between the inductor and capacitor, storing and transferring energy between them. Because such a circuit acts as a kind of storage vessel for electric energy, it is often referred to as a tank circuit. A tank circuit can also be called as an LC circuit, and the circulating current is referred to as the tank current. And that concludes my report.
Let's continue. I am Jan Matthew Robert M. Cantos, and I will discuss 2-3 and 2-4. Filters. What is a filter? A filter is a frequency selective circuit that pass certain frequencies and reject others. It is a device or material for suppressing or minimizing waves or oscillations of certain frequencies as of electricity, light, or sound. A filter is an electronic device that can remove specific range of frequencies from a signal. A filter could be active or passive. Passive filters. Passive filters are created using components such as resistors, capacitors, and inductors that do not amplify. On the other hand, active filters use amplifying devices such as transistors and operational amplifiers. The main difference between active and passive filters is that passive filters cannot cause a power gain. They cannot bring energy into the circuit, nor it can regulate the current. An active filter can add energy into the current and also control the current. An electric filter is a network designed to attenuate certain frequencies but pass others without attenuation. A filter circuit, therefore, possesses at least one band, a band of frequencies in which the output is approximately equal to the input, and an attenuation band in which output is zero. There are five basic kinds of filter circuits. First is the low-pass filters. Low-pass filters only pass frequencies below a critical or cutoff frequencies. These cutoff frequencies are the frequencies that separate the different pass and attenuation bands. Second, high-pass filters. High-pass filters only pass frequencies above the cutoff frequency. Third, band-pass filters. Band-pass filters pass frequencies over a narrow range between lower and upper cutoff frequencies. Next is band-reject filters. It rejects or stops frequencies over a narrow range between lower and upper cutoff frequencies. And last, all-pass filters. It passes all frequencies over a desired range but have a predictable phase shift characteristics. RC RC filters. A resistor capacitor circuit, RC circuit, or RC filter, or RC network. It is an electric circuit composed of resistors and capacitors driven by a voltage or current source. RC filters use combinations of resistors and capacitors to achieve a desired frequency response. A first-order RC circuit is composed of one resistor and one capacitor and is the simplest type of RC circuit. Most RC filters are the low-pass or high-pass type. Any low-pass or high-pass filter is effectively a frequency-dependent voltage divider. RC circuits can be used to filter a signal by blocking certain frequencies and passing others. An RC coupling circuit is a high-pass filter because the AC input component is developed across the resistor while DC voltage is blocked by a capacitor. The two most common RC filters are the low-pass filter and the high-pass filters. Low-pass filter. A low-pass filter is a circuit that introduces no attenuation at frequencies below the cutoff frequency, but completely eliminates all signals with frequencies above the cutoff. Low-pass filters are sometimes referred to as high-cut filters. The cutoff frequency of a filter is that point where the resistance R and a capacitive reactance Xc are equal. We can see in the image the RC circuit and the RC low-pass filter graph. In the circuit, there is the resistor variable and the capacitor variable. The cutoff frequency of a filter is that point where the resistance and the capacitive reactance are equal. Next, we have the high-pass filters. A high-pass filter passes frequencies above the cutoff frequency with little or no attenuation, but greatly attenuates those signals below the cutoff. The basic high-pass filter is a voltage divider with a capacitor serving as the frequency-sensitive component. A high-pass filter can be implemented with a coil and a resistor. Here we have two kinds of high-pass filter circuits. First, the RC high-pass filter circuit, and second, the RL high-pass filter circuit. Given on a RC high-pass filter circuit, we have a resistor and a capacitor. On an RL high-pass filter circuit, we also have a resistor variable, but instead of having a capacitor variable, we have an inductor variable. An inductor is also called a coil or a choke. It is a winding of multiple turns of wire to increase the power factor. Another kind of RC filter is the RC notch filter. Notch filters are also called band stop or band reject filters. Notch filters attenuate a narrow range of frequencies around a center point frequency. A simple notch filter implemented with resistors and capacitors is called a parallel T or twin T filter. The center notch frequency is calculated by the formula F notch is equal to 1 over 2 pi RC. Here, we can see the RC notch filter circuit on the left side and the RC notch filter graph on the right side. It says that the RC notch filter is implemented with resistors and capacitors and is calculated by the formula F notch is equal to 1 over 2 pi RC. On the graph given, we can see that the frequencies has a center point which is also called the F notch. Another kind of filter is the LC filter. An LC circuit, also called a resonant circuit, tank circuit, or a tuned circuit. It is an electric circuit consisting of an inductor, represented by letter L, and a capacitor, represented by the letter C, connected together. The circuit can act as an electric resonator, an electrical analog of a tuning fork, storing energy oscillating at the circuit's resonant frequency. LC circuits or filters are used in either for generating signals at a particular frequency or picking out a signal at a particular frequency from a more complex signal. LC filters use combinations of inductors and capacitors to achieve a desired frequency response. They are typically used with radio frequency (RF) applications. LC filter terminologies. Passband. Passband is the frequency range over which the filter passes signals. It is the range of frequencies or wavelengths that can pass through a filter. For example, a radio receiver contains a bandpass filter to select the frequency of the desired radio signal out of all the radio waves picked up by its antenna. The passband of a receiver is the range of frequencies it can receive. Stopband. Stopband is the range of frequencies outside the passband. That is, the range of frequencies that is greatly attenuated by the filter. Stopband is a band of frequencies between specified limits through which a circuit, such as a filter or telephone circuit, does not allow signals to pass, or the attenuation is above the required stopband attenuation level. Depending on application, the required attenuation within the stopband may be typically a value between 20 and 120 decibels higher than the nominal passband attenuation, which often is 0 decibel. Attenuation. Attenuation is the amount by which undesired frequencies in the stopband are reduced. Attenuation is a general term that refers to any reduction in the strength of a signal. Attenuation occurs with any type of signal, whether digital or analog. Sometimes called loss, attenuation is a natural consequence of signal transmission over long distances. Insertion loss. Insertion loss is the loss the filter introduces to the signals in the passband. Passive filters introduce attenuation because of the resistive losses in the components. Insertion loss is typically given in decibels. Impedance. Impedance is the resistive value of the load and source terminations of the filter. Filters are usually designed for specific driving source and load impedances that must be present for proper operation. Ripple is a term used to describe the amplitude variation with frequency in the passband. Amplitude variation with frequency in the passband or repetitive rise and fall of the signal level in the passband of some types of filters is known as a ripple. It is usually stated in decibels. There may also be ripple in the stop bandwidth in some types of filters. Shape factor. Shape factor is the ratio of the stop bandwidth to the pass bandwidth of a bandpass filter. It compares the bandwidth at minimum attenuation, usually at the -3 decibel points or cutoff frequencies, to that of maximum attenuation and thus gives a relative indication of attenuation rate or selectivity. The smaller the ratio, the greater the selectivity. The ideal is a ratio of 1, which in general cannot be obtained with practical filters. A pole. A pole is a frequency at which there is a high impedance in the circuit. It is also used to describe one RC section of a filter. Zero. Zero is a term used to refer to a frequency at which there is a zero impedance in the circuit. Envelope delay or time delay is the time it takes for a specific point on an input waveform to pass through the filter. Roll-off, or attenuation rate, is the rate of change of amplitude with frequency in a filter. The faster the roll-off, or the higher the attenuation rate, the more selective the filter is. The better able it is to differentiate between two closely spaced signals, one desired and the other not. The major types of LC filters in use are named after the person who discovered and developed the analysis and design method for each filter. The most widely used filters are Butterworth, Chebyshev, Hauer, and Bessel. Each can be implemented by using the basic low and high pass configurations shown previously. The different response curves are achieved by selecting the component values during the design. Butterworth. The Butterworth filter effect has maximum flatness in response in the passband and a uniform attenuation with frequency. The attenuation rate just outside the passband is not as great as can be achieved with other types of filter. Chebyshev. Chebyshev filters have extremely good selectivity. Their attenuation rate or roll-off is high, much higher than that of Butterworth filter. The attenuation just outside the passband is also very high, again, better than of the Butterworth. The main problem with the Chebyshev filter is that it has ripple in the passband, at, as is evident from the figure. The response is not flat or constant, as it is with the Butterworth filter. This may be the disadvantage in some applications. Cower or elliptical filter. Cower filters produce an even greater attenuation or roll-off rate than do Chebyshev filters and greater attenuation out of the passband. However, they do this with an even higher ripple in the passband as well as outside of the passband. Bessel or Thomson filters. Bessel circuits provide the desired frequency response but have a constant time delay in the passband. Bessel filters have what is known as a flat group delay. As the signal frequency varies in the passband, the phase shift or time delay it introduces is constant. In some applications, constant group delay is necessary to prevent distortion of the signals in the passband due to varying phase shifts in the frequency. Filters that must pass pulses or wideband modulations are example. To achieve this desired response, the Bessel filter has lower attenuation just outside the passband. Here, we can see the Butterworth elliptical or Cower, Bessel or Thomson, and the Chebyshev response curves. An older but still useful filter is the mechanical filter. A mechanical filter uses resonant vibrations of mechanical disks to provide the selectivity. The signal to be filtered is applied to a coil that interacts with a permanent magnet to produce vibrations in the rod connected to a sequence of 7 or 8 disks, whose dimensions determine the center frequency of the filter. The disc vibrates only near the resonant frequency, producing movement in another rod connected to an output coil. This coil works with another permanent magnet to generate an electrical output. Mechanical filters are designed to work in the 200 to 500 kHz range and have very high Qs. Their performance is comparable to that of crystal filters. Bandpass filters, configured with series or parallel resonant circuits, allow a narrow range of frequencies around a center frequency to pass with minimum attenuation but rejects frequencies above and below this range. Two types of bandpass filters are shown in Figure 2-36. In Figure 2-36A, a series resonant circuit is connected in series with an output resistor, forming a voltage divider. At frequencies above and below the resonant frequency, either the inductive or the capacitive reactance will be high compared to the output resistance. Therefore, the output amplitude will be very low. However, at the resonant frequency, the inductive and capacitive reactance cancel, leaving only the small resistance of the inductor. Thus, most of the input voltage appears across the larger output resistance. The response curve for this current is shown in Figure 2-35B. A parallel resonant bandpass filter is shown in Figure 2-36B. Again, a voltage divider is formed with resistor R and the tuned circuit. This time, the output is taken from across the parallel resonant circuit. At frequencies above and below the center resonant frequency, the impedance of the parallel tuned circuit is low compared to that of the resistance. Therefore, the output voltage is very low. Frequencies above and below the center frequency are greatly attenuated. At the resonant frequency, the reactants are equal and the impedance of the parallel tuned circuit is very high compared to that of the resistance. Therefore, most of the input voltage appears across the tuned circuit. The response curve is similar to what is shown in Figure 2-35B. Band reject filters, also known as band stop filters, reject a narrow band of frequencies around a center or notch frequency. Two typical LC band stop filters are shown in Figure 2-39. In Figure 2-39A, the series LC resonant circuit forms a voltage divider with input resistor R. At frequencies above and below the center rejection or notch frequency, the LC circuit impedance is high compared to that of the resistance. Therefore, signals at frequencies above and below center frequency are passed with minimum attenuation. At the center frequency, the tuned circuit resonates, leaving only the small resistance of the conductor. This forms a voltage divider with the input resistor. Since the impedance at resonance is very low compared to the resistor, the output signal is very low in amplitude. A parallel version of this circuit is shown in Figure 2-39B, where the parallel resonant circuit is connected in series with a resistor from which the output is taken. At frequencies above and below the resonant frequency, the impedance of the parallel circuit is very low. There is, therefore, little signal attenuation and most of the input voltage appears across the output resistor. At the resonant frequency, the parallel LC circuit has an extremely high resistive impedance compared to the output resistance, and so minimum voltage appears at the center frequency. LC filters used in this way are often referred to as traps. Active filters. Active filters are frequency-selective circuits that incorporate RC networks and amplifiers with feedback to produce low-pass, high-pass, bandpass, and bandstop performance. These filters can replace standard passive LC filters in many applications. They offer the following advantages over standard passive LC filters. Gain. Gain because active filters use amplifiers. They can be designed to amplify as well as filter, thus offsetting any insertion loss. Second, no inductors. Inductors are usually larger, heavier, and more expensive than capacitors and have greater losses. Active filters use only resistors and capacitors. Third, easy to tune. Because selected resistors can be made variable, the filter cutoff frequency, center frequency, gain, Q, and bandwidth are adjustable. Fourth, isolation. The amplifiers provide very high isolation between cascaded circuits because of the amplifier circuitry, thereby decreasing interaction between filter sections. Fifth and last advantage is easier impedance matching. Impedance matching is not as critical as with LC filters. A special form of active filter is the variable state filter, which can simultaneously provide low pass, high pass, and band pass operation from one circuit. Crystal and ceramic filters. Crystal and ceramic filters are made of thin slivers of quartz crystal or certain other types of ceramic materials. Crystals and ceramic elements are widely used in oscillators to set frequency of operation to precise value, which is held despite temperature and voltage variations that may occur in the circuit. Crystals and ceramic elements are also used as circuit elements to form filters, specifically bandpass filters. The equivalent circuit of a crystal or ceramic device is a tuned circuit with a Q of 10,000 to 1 million, permitting highly selective filters to be built. The equivalent circuit and schematic symbol of a quartz crystal are shown in Figure 2-46. The crystal acts as a resonant LC circuit. The series LCR part of the equivalent circuit represents crystal itself, whereas the parallel capacitance CP is the capacitance of the metal mounting plates with the crystal as dielectric. Here is a schematic symbol for a ceramic filter. Crystal and ceramic filters. The surface acoustic wave filters. The surface acoustic wave or SAW filter is a special form of crystal filter designed to provide the exact selectivity required by a given application. SAW filters are normally used at very high radio frequencies where selectivity is difficult to obtain. They are widely used in modern TV receivers, radar receivers, wireless LANs, and cell phones. In Figure 2-51 shows the schematic design of a SAW filter. SAW filters are made on a piezoelectric ceramic substrate such as lithium niobate. A pattern of interdigital fingers on the surface converts the signal into acoustic waves that travel across the filter surface. By controlling the shapes, sizes, and spacings of the interdigital fingers, The response can be tailored to any application. Interdigital fingers at the output convert the acoustic waves back to electrical signals. Switch capacitor filters. Switch capacitor filters, SCFs, also known as analog sample data filters or commutating filters, are active IC filters made of op-amps, capacitors, and transistor switches. They provide a way to make tuned or selective circuits in an IC without the use of discrete inductors, capacitors, or resistors. The secret to the SCF is that all resistors are replaced by capacitors that are switched by MOSFET switches. Resistors are more difficult to make in IC form and take up far more space on the chip than transistors and capacitors. With switch capacitors, it is possible to make complex active filters on a single chip. Other advantages are selectivity of filter type, full adjustability of the cutoff or center frequency, and full adjustability of bandwidth. One filter circuit can be used for many different applications, can be set to a wide range of frequencies and bandwidths. The basic building block of SCFs is the classic op-amp integrator as shown in Figure 2-52A. The input is applied through a resistor and the feedback is provided by the capacitor. With this arrangement, the output is a function of the integral of the input Vout is equal to negative 1 over RC integral of V in dt. With AC signals, the circuit essentially functions as a low-pass filter and a gain of 1 over RC. To work over a wide range of frequencies, the integrator RC values must be changed, making low and high resistor and capacitor values in IC form is difficult. However, this problem can be solved by replacing the input resistor with a switch capacitor as shown in Figure 2-52B. The MOSFET switches are driven by a clock generator whose frequency is typically 50 to 100 times the maximum frequency of the AC signal to be filtered. The resistance of a MOSFET switch when on is usually less than 1000 ohms. When the switch is off, its resistance is many mega ohms. An interesting variation of a switch capacitor filter is the commutating filter shown in Figure 2-53. It is made of discrete resistors and capacitors with MOSFET switches driven by a counter and a decoder. The circuit appears to be a low-pass RC filter, but the switching action makes the circuit function as a band-pass filter. The operating frequency Fout is related to the clock frequency Fc and the number N of switches and capacitors used. The operating waveforms in Figure 2-53 show that each capacitor is switched on and off sequentially so that only one capacitor is connected to the circuit at a time. A sample of the input voltage is stored as a charge on each capacitor as it is connected to the input. The capacitor voltage is the average of the voltage variation during the time the switch connects the capacitor to the circuit. The mathematical analysis of the modulation and multiplexing methods used in communication systems assumes sine wave carriers and information signals. This simplifies the analysis and makes operation predictable. However, in the real world, not only information signals are sinusoidal. Information signals are typically more complex voice and video signals that are essentially composites of sine waves of many frequencies and amplitudes. Information signals can take of an infinite number of shapes, including rectangular waves, triangular waves, sawtooth waves, and other non-sinusoidal forms. Such signals require that a non-sine wave approach to be taken to determine the characteristics and performance of any communication circuit or system. It is called the Fourier analysis. The Fourier theory states that a non-sinusoidal waveform can be broken down into individual harmonically related sine wave or cosine wave components. The classical example of this is a square wave, which is a rectangular signal with equal duration, positive and negative alternations. A harmonic is a sine wave whose frequency is some integer multiple of a fundamental sine wave. For example, the third harmonic of a 2 kHz sine wave is a sine wave of 6 kHz. Figure 2-57 shows the first four harmonics of a fundamental sine wave. What Fourier theory tells us is that we can take a non-sinusoidal waveform and break it down into individual harmonically related sine wave or cosine wave components. The classic example of this is a square wave, which is a rectangular signal with equal duration, positive and negative alternations. In figure 2-58, this means that T1 is equal to T2. Another way of saying this is that the square wave has a 50% duty cycle D, the ratio of the duration of the positive alteration T1 to the period capital T expressed as a percentage. D is equal to T1 over capital T times 100. Fourier analysis tells us that a square wave is made up of a sine wave at the fundamental frequency of the square wave plus an infinite number of odd harmonics. For example, if the fundamental frequency of the square wave is 1 kHz, the square wave can be synthesized by adding the 1 kHz sine wave and harmonic sine waves of 3 kHz, 5 kHz, 7 kHz, 9 kHz, and many more. Fourier analysis allows us to determine not only sine wave components in a complex signal, but also a signal's bandwidth. Time domain versus frequency domain. Most of the signals and waveforms that we discuss and analyze are expressed in the time domain. That is, they are variations of voltage, current, or power with respect to time. A frequency domain plots amplitude variations with respect to frequency. Fourier theory gives us a new and different way to express and illustrate complex signals. Here, complex signals containing many sine or cosine components are expressed as sine or cosine wave amplitudes at different frequencies. In other words, a graph of a particular signal is a plot of sine or cosine components amplitudes with respect to frequency. Figure 2-63 shows how the time and frequency domains are related. The square wave discussed earlier is used as an example. The result is a three-axis, three-dimensional view. Signals and waveforms in communication applications are expressed by using both time domain and frequency domain plots, but in many cases, the frequency domain plot is far more useful. This is particularly true in the analysis of complex signal waveforms as well as the many modulation and multiplexing methods used in communications. Test instruments for displaying signals in both time and frequency domains are readily available. You are already familiar with the oscilloscope, which displays the voltage amplitude of a signal with respect to the horizontal time axis. Here is figure 2-61, a common non-sinusoidal wave and their Fourier equations. The test instrument for producing a frequency domain display is the spectrum analyzer. Like the oscilloscope, the spectrum analyzer uses a cathode ray tube for display, but the horizontal sweep axis is calibrated in hertz and the vertical axis is calibrated in volts or power units or decibels. It is the key test instrument in designing, analyzing, and troubleshooting communication equipment. Thank you for listening. This is presented by David Angelo Bantugon and John Matthew Robert M. Cantos from ICE 3301. Thank you.